Hello, everyone. I hope you still have some energy left after already a relatively long day of talks. I'm Stephan Herhut, and I'm a member of the team at Intel Labs that works on Tral or parallel JavaScript. And I started about 3 years to look into JavaScript. And we were looking at the time at what could we bring to JavaScript, what could we help to make it better. And one thing I'm personally interested in is in concurrent programming and parallel programming. So that was kind of an obvious choice of what I should look at. So of course, if you come new to a language, you have to look what's there, how things work, what the current state of the art is. Being very new to JavaScript, I invested some time at the very beginning, 3 years ago, to actually understand what is there. And I've been fascinated since by developments that have appeared in that kind of sphere. So what I want to do in this talk today is I want to share with you a little bit of what I found interesting, what I found fascinating when I looked at concurrency and parallel computing in JavaScript. So this is by no means meant to be complete, right? So there's a lot more stuff going on, and you cannot talk about everything that happens on concurrency and parallel computing in JavaScript in 40 minutes. So this is a very personal selection. So if your most favorite thing is not in here, please don't be disappointed. It's just what I found most interesting. So I thought to start this off, to make sure that we all know what I'm talking about, I wanted to give you an idea of what I mean if I say concurrency and parallel computing, because my title is concurrency and parallel computing. So why is there two things in there? And the answer is because they're not the same. And this is actually quite tricky. So a lot of people use these interchangeably. They say concurrency when they need parallelism, and they say parallelism when they mean concurrency. So just to make clear what I think each of these two is, I thought I'd start off with giving you my very personal definition of what the two are, which is kind of a combination of what you will find on the web, spiced up with my personal opinion. OK, let's start. So what's concurrency? And here's the definition I came up with. Concurrency is if you perform multiple tasks at the same time, and you possibly interleave them, but you're a single actor, right? There's only one entity that does something. That's concurrency. And my favorite concurrent system, which I've been fascinated by ever since I was a child, are these one-man bands, right? So that's a concurrent system. You have one actor, which is the musician, and he's doing a lot of things interleaved to make a song come out of the end. So whenever I say concurrent system, this is what I want you to have in mind. Right? So this is the picture I want you to think. This is concurrent system. OK, so when this is concurrent system, what then is a parallel computing? What's a parallel system? And here's my try of giving you a definition of what parallel computing is. So parallel computing is if you have multiple entities working at the same time, and they do one or multiple tasks. So other than concurrency, now you have multiple entities working on something. And I also tried to come up with a nice picture that you can have in mind whenever I say a parallel system. And here's an example. It's car manufacturing, right? So you have these multiple workers, and each of them is building a car, right? So they're all doing the same tasks, which is building a car. But they're building multiple cars at a time, and there's multiple entities working at a time. So this is an example of a parallel system. This is parallel computing. So whenever I say parallel computing, think of this picture, right? So these are the two things I want to talk about today, about concurrency and parallelism in JavaScript. So here's an agenda, just so you know what to expect. First of all, I will talk about concurrent systems and concurrent programming. And you, I assume, are all web developers. So you're experts in writing concurrent systems. You might not know it, but you really are. Because in JavaScript, you have this event-driven asynchronous programming model, and that's all about interleaving different tasks while only having one entity, your web browser, actually computing. I will also talk a little bit about promises, because I think promises really make developing asynchronous systems a lot easier. So promises are a great API and a great technique to cope with the complexities of asynchronous systems. And lastly, I will talk about web workers, probably the veteran technique in web browsers when it comes to concurrency, but you have to mention them. So web workers are there in your browser, and you should make use of it. So I will talk a little bit about why you need web workers and conceptually what they're good at. The second half of this talk is about parallel computing. And this is motivated by the fact that if you look at today's hardware, there's a lot of parallel hardware in your devices, no matter what kind of device you use. Right? Whether it's a laptop or a mobile phone or a desktop or a supercomputer, it doesn't really matter. You will always have parallel hardware in there. So I will talk about three flavors that I think are most interesting to web developers. The first thing I want to talk about is SIMD units, because that's something that's in every platform. Right? Every modern processor has a SIMD unit, and there's work going on to bring that to JavaScript. So I will give you a flavor of what SIMD programming looks like, or could look like in JavaScript. The second thing you have in all your systems today is multi-core processors. Right? Even mobile phones have multi-core processors. So you should make some good use of them. And I will talk about two approaches, what to do about these multi-cores. And lastly, you have programmable GPUs. And that's, of course, what's most close to my heart, because that's what we designed Tral for, multi-core and GPU. So I will talk a little bit about what Tral is about, what the motivation is, and what you can do with it and how you use it. So that's the agenda. OK. Without further ado, let's get into it. So concurrency. Let's talk about concurrency. So before I go into anything new or flashy, I want to make sure that we all are on the same page in understanding the JavaScript execution model and where the concurrency is in that model. So if you look at JavaScript, it's a very, very nice execution model you have. So if you compare yourself to C developers, C++ developers that have to write multi-thread applications, you're in a really nice spot in JavaScript. Because you have this single event queue, that's all you have to wonder about. That's what steers execution. And all events always run to completion. So at no time will your event handler be interrupted for something else to happen. So you never have to think about these interleavings. It's just my event handler runs to completion, and then the next event handler comes. That's a very powerful model. You may create new events from your existing events. Right? That allows you to create new concurrency. That makes this actually feasible to use as a concurrent programming platform. And the only caveat in this entire system is that your event ordering is non-deterministic. So that's the only thing that makes it slightly complicated. Whenever you enqueue a new event, you don't know when it will actually be processed. Likewise, by the nature of web browsers, you never know when an external event will happen, right? The user is very non-deterministic. You never know when he will click. The network is non-deterministic. You never know how fast your connection is. So all these events happen at a, for you, perceived random order, and you have to kind of cater for that. So that's the most complicated part about writing asynchronous programs, is dealing with this non-determinism of order. Other than that, this is a great, great environment to be in. Throughout this talk, I will use some graphical pictures to explain some concepts. And this is what it essentially looks like. So I will use this event queue, that's this long blue line here, with the boxes, which are your events. Right? The color typically doesn't mean anything. It's mostly there because it looks nice. And at the very bottom, you have this arrow, and that tells you where execution currently is. Right? So that's my abstract model of execution in JavaScript. OK, so let's do an example. I thought about what's the most simple example can do about an asynchronous system. And I went to Stack Overflow, which is the source of examples. And I came up with asynchronous image loading. So I hope you can read that all the way in the back. But essentially what this does is you create an image here, an image object. And you assign this URL. Oh, here's my execution mode. Sorry. You assign this URL up here that tells your image object what image to load over the network. And the second thing you do sorry, let me go back. The second thing you do is you create this event handler here, right? So you assign to the image onload a function that is called once the image has been loaded and then does something. In this example, it will add the image to your container. Right? So this is asynchronous image loading. The idea is the image is loaded in the background, and once it's available, it will be inserted into the page. That's the fancier version of having the browser display some placeholder while you're loading. So how does this run at execution time? So execution JavaScript, it's run to completion, top to bottom. So execution starts up here, and eventually it will reach this line, which will tell the browser, OK, load the image located at this URL. Right? Eventually, the image will have been loaded. That's when this onload event here is fired, and execution reaches this point. And that's where asynchronicity comes in. So this is after this code has completed, the image has been loaded, then your callback, which is this function here, will be called. Right? So that's a very straightforward way of doing asynchronous image loading. Anyone in the room here that sees a problem with this kind of code?
You all know that we actually come too late, but in actually it's the same active thread. So the image loading will not start it even to finish this thread.
Yeah, that's a good comment. So the comment here is, what you're doing, you're first assigning the URL, which will spawn off the loading of your image. Maybe by the time you get to assign your callback here, the image has already been loaded, and that callback has already happened. So your code will never be executed. Right? That's because the loading of the image might happen in a background thread. So that's a race condition you could have here. Now, there's two stories I have been told. The one story is, by the definition of the standards, even though this image might have been loaded, the event will still call the callback that's valid at the end of this script. That's how it's meant to be. However, if you look on the web for people having issues with these kinds of orderings, there are always bugs creep up in browsers that will still make this event not being called. So if you really want to make sure that your code is actually executed, one tip you will see is that you have to make sure that your callback is defined before the event can happen. Right? That's the gospel of asynchronous programming. Always make sure your callback is defined before the event happens. Now, this is just for warm-ups. A different way to look at this, and that's where it really becomes interesting. You can see this as an asynchronous flow. So the idea on this slide is you first render your generic image, your generic website. That happens first. Then the image will be loaded. That's what's triggered by this code snippet here. Right? You assign the onload, you assign the URL, and you have assigned your inload callback. This will trigger the loading of the image. Eventually, that image will have loaded, and you will call the callback to actually render the image. Right? So you can see this as an asynchronous flow. This is how your execution flows. And you encode this dependency here between loading the image and actually rendering the image by using your callback. Right? So this is just a graphical representation of this code. Okay? As I said, this is a very, very simple example. Real-life applications typically are way more complex. So I tried to come up with an example that's more complex, but still easy to explain on a couple of slides. And here it is. So what this is, it's a flow of an asynchronous website. And the idea is you want to do some personalization of your website. So you want to first render a standard website so that your user sees something and has something to interact with right away. And then you want to asynchronously load more information and to personalize that experience. So one way to do this is you first render your generic website. That's the yellow box on the top. And then you spawn off an asynchronous event that will look up a person's profile. Right? That's a network request. You get back the profile from your own server or maybe some third-party server, and then you want to use that profile information to grab some auxiliary information. Like you could load an avatar image. You could load some social status. You could look up some recent activity. Right? Those are further asynchronous callbacks. And eventually, once all these callbacks have completed, you can create the personal view and render the updated web page. I know there's many other ways to do this, but let's stick to this as an example. So if you want to do this, you will end up with a lot of callbacks, with a lot of implicit dependencies scattered throughout your code if you write this naively. But it's still manageable, right? You only have 1, 2, 3, 4, 7 callbacks to encode. What I think makes this really complicated is once you have to handle error. Because errors have this property that they just occur anywhere in your code, right? So the rendering of the website could fail. The lookup of the person information could fail. Any of your loading of the status could fail. Even creating the personal view could fail for some reason. So error can happen anywhere in this graph. But typically, you don't care about the error. What you really care about is the end result. So your error handler will typically be at the very end of this asynchronous flow. At the very end, you will say, OK, something went wrong. I cannot render a personal view. You don't actually care about what went wrong up to this point. If you have to encode this in callbacks, you end up with a lot more callbacks in your graph. Because now, for every error, you have to go to your handler somehow. And this is the point when your code really becomes messy. This is the point when it really becomes hard to understand what the code actually does, where it goes, what the dependencies are. And this is where I believe promises come in really nicely. This is, for me, what promises are all about. So promises. What are promises? I see promises as a way to directly encode the asynchronous flow of your application in data instead of having these callbacks in your code. So essentially what you do is you have promise objects, and they encode the state of an asynchronous operation, whether it's still pending or whether it has completed. You have some methods on these objects that allow you to encode dependencies. Like you have a sequence, something has to start after something else. Or you have joins. Once all this has completed, I want to do something else. And the really important thing, I believe, is errors simply propagate along these flows without you having to do anything about it. And that's very, very powerful. So let's look at the example. Now, promise style. Right? So the basic graph stays exactly the same because your application hasn't changed. The interesting is, how do I encode this? And I can now just write this graph in code. So I start with my render promise. So I call this method render, which renders my generic website. And it returns to me a promise, an object that encodes the state of this rendering operation. And this state, as I said, this object has 3 states. It can be pending, which means the operation has not yet completed. It can be fulfilled, which means the operation has completed, so whatever is coming after it can now start. Or it can be rejected, which means something went wrong somewhere up the stream. So with this, I can now encode the rest of my graph. So I want to do the lookup after I did the render. So I encode this by writing this render promise.then, which means once my render promise is completed, then I want to call the lookup. And that doesn't actually perform the lookup. It just returns me another promise. Likewise, I can encode the 3 operations I do to actually load social status. Right? So the avatar happens after the lookup is complete, and the social happens after the lookup is complete. And the recent happens after the lookup is complete. So that encodes the 3 edges in my graph. And lastly, and this is an operation I borrow from When.js here, when all of the avatar loading, the social loading, and the recent loading have completed, then I want to create my website, my personalized view of the website. So this is very nicely encapsulated. I believe it's very easy to understand. So if you look at this code, you know right away how this application behaves. But what's really the killer is, let me add error handling to it. This is with error handling. Let me highlight the change in code. Right? It's that little thing there. Because you only have to handle the error where you actually care about it. It will be automatically propagated along your entire promises flow up to the point where you have a handler. And that's all you need to do. So this is very easy to understand. This is very powerful. And it takes a lot of the pain out of writing asynchronous programs. So if you want to know more about promises, there's a lot available on the web. So there's the A+ spec, which is community effort to come up with a joint specification for promises, because by now they're actually widespread across APIs. There's when.js, which adds another nice little layer on top. And jQuery also has something like promises, which is deferred objects. So they're everywhere. So promises will come to you if you work in web development. Just understand how powerful they are for error handling. So let's look at something else. This is probably a window all of you have seen in some form or other. I blacked out the actual URL because I didn't want to embarrass someone here. But this is the, ooh, your script is running too long warning. And every browser has it. And typically this happens when you have some script that's running too long because it's doing too much. And it blocks your browser UI because you have this single event queue. Your browser cannot do anything else whilst your event is running. So what do you do about this? How do you handle long-running scripts? So the underlying problem is only one event executes at a time, and no event is ever interrupted. So how do we solve this? What do we do about it? This is your scenario in the graphical way. You have your first event, and then you have this super long event, and then all the other events queue up behind it. How do we break this long event such that the events behind it can actually be processed, and the browser as a whole can make progress? And that's where web workers come into the game. Web workers are a great way to have a finer granular scheduling in your concurrent system, because JavaScript schedules at an event level. So there's always one event, and it runs to completion. If you want to break this, if you want to have actually multiple events running interleaved, that's where web workers come in, because they allow you to spawn another JavaScript engine, essentially, which is separated from the existing engine, but they can communicate via messages with each other. So this is what the picture looks like. If we add another message queue and a web worker. So what you now can do is, instead of having this long-running event block up your event queue, you can just send a message to your worker telling him what to do. The worker will run this, whilst the main event queue can make progress on running the other events. And eventually, once the long-running event has completed, your long-running script is completed, it will send a message back to your main event queue, which you can then catch and handle. As I said before, this is about concurrency. So there's no parallelism here. It doesn't actually mean that these things run at the same time. All this does, it allows your operating system to interleave them. So now the operating system scheduler may run a little bit of this, jump to the other one, run a little bit of that, jump back, right? You get interleaving. And that's what allows you to hide the latency of this long-running task, even on a single core system. So that's where web workers come into the picture. OK, so that's all I wanted to say about concurrency. Let's switch minds and go to parallel computing. So what do we have to do? What techniques, methods do we have for parallel computing in JavaScript? As I said before, you have all this parallel hardware. It's ubiquitous. It's everywhere. And if you really want to have the best experience on whatever platform, maybe not today, but certainly in the future, you will have to make use of this hardware. Because native applications do it already. Right? Native applications make use of SIMD. They make use of programmable GPUs. They make use of multi-core. So eventually, web applications will have to catch up. So now is the time where this future is shaped, where all the techniques are developed. And now is the time to also get involved. So if you talk about parallel hardware, of course, you also have to talk about web workers. I said web workers are for concurrency, but if you actually are on a multi-core system, so you have 2 cores, nothing stops your operating system from actually running the 2 threads on different cores. Right? So it may run your web worker on a different core than your main event queue. And this actually gives you parallel execution. The thing here is you don't know. Right? So as a web developer, you don't know whether there are 2 cores. You don't know whether the operating system will do that. You just don't know. But it may do so. So web workers are a way to do parallel programming in JavaScript. but you have very little control about whether you actually are running in parallel or not. So what happens if we have two web workers? Well, essentially, you just get a second execution engine. And now these things really run in parallel. That's just an aside to complete web workers. What I find really exciting that's now coming to JavaScript is SIMD programming. So what is SIMD programming? I thought maybe web developers are not too familiar with doing SIMD programming. So let's do a little SIMD primer. So SIMD stands for single instruction, multiple data. So typically, you have small vectors of numbers, and you perform the same operation on them. Like you add two vectors, or you multiply two vectors element-wise. And what makes this really tricky is that you cannot really have control flow in SIMD operations. Control flow is like having a conditional, because all the SIMD execution always does the same operation. Right? So if you want to add one half of a vector to one half of another vector and the other half to another half of another vector, you cannot express that as a conditional, because that would break this all execution does the same thing. So you have to do some trickery to get around this lack of control flow. And that's what makes SIMD programming actually challenging. Right? Programming on vectors is easy. If there would be control flow, it would be all like ordinary programming. So that's the main big difference. So let's do some examples. Let's see whether you're still energetic. So here are two SIMD vectors for you, 1, 2, 3, 4, and 2, 3, 4, 5. And there's this magic SIMD operation add. Anyone has an idea what the result might be? Yeah. So there's some people are still awake. How about this one? 1, 2, 3, 4, 2, 3, 4, 5, and now you apply the AND operation, the bitwise AND. I'm just kidding. So nobody wants to do this in the head, but yeah, so that's another operation you have, right? You can do bitwise AND operations. You also have comparison operations. So those are somewhat interesting, right? If you do a less than on two vectors, you don't get a single result, but you get actually a vector of results. So if you do the less than here of 1, 2, 3, 4, and 4, 3, 2, 1, you get true, true, false, false. So everything computes on vectors. I said that there is no control flow. So the way around this is you have to model control flow and data flow. And for that, you have also a range of operations you can use. Select is one of them. So what does select do? Select takes 3 arguments. The first one is a vector of Booleans, followed by 2 vectors of numbers. And what select does is, depending on the value in the first vector, it will pick a value from the second or third argument, right? So down here, we have true, false, true, false. So that will take the first element from the first vector, second element from the second vector, third element from the first vector again, and so forth. And this allows you to blend multiple results into a combined result. And as we will see later, that's a good way to encode control flow. This is the result. Another operation you have is shuffle. So what does shuffle do? Shuffle essentially allows you to take elements from a vector and reorder them. It's like a permutation operation. So in this case here, that's the result. So it says the first element of the result will be the 4th element of the argument. Right? Indexing is from 0. The second element of the result will be the 3rd element from the second argument, and so forth. Right? So it allows you to blend, to mix up elements from the vector. And this is really all you have in SIMD programming. So what does this have to do with JavaScript? Well, there's a proposal by John McCutcheon, I hope I pronounced his name right, to add this programming model to JavaScript. And the idea how to do this, essentially you add special types for these vectors, like you get float force, float 32 times 4, and int 32 times 4. Those are your vector types. And they also get SIMD-style accessors. So if somebody of you already has done some WebGL programming or other SIMD-style programming, you typically get accessors like X, Y, Z, W for the 4 elements. So you also get that here. And the other important thing is you get an array of these vectors. So you get a float 32 times 4 array. This is like a typed array, but it stores vectors instead of single floats. And then you add a SIMD object, very similar to what you have with the math object in JavaScript already, which gives you all these operations like add, subtract, multiply, divide, and so on. So essentially all the operations I showed before and some more. And with this, you can then write SIMD code in JavaScript. So let me give you an example of what this looks like. Here's a very simple piece of JavaScript code. Let's assume we have two arrays, A and B, and they're both float 32. And what I'm doing here is I just have a loop that iterates over the entire length of the array and adds up the elements from both arrays and writes them into a result array, X, which is also a float 32. Right? So this is very straightforward, adding elements of two arrays. With the SIMD extension, we can also write the SIMD style. So now we have two arrays A and B, and they are float 32 times 4 arrays. So they are now arrays of vectors. And all that changes in your loop, essentially, is that you now use this simd.add, which reads A of I and B of I, which are two vectors, and produces a vector as a result, which is then written into array X. And X, again, is a float 32 times 4 array. There is a slight difference between the semantics of these two codes. Obviously, the left-hand side works on scalar single values, and the right-hand side works on vectors. But there's another difference. On the left-hand side in JavaScript, although the values are stored inside a float 32 array, once they are read, they turn into doubles. Because every number in JavaScript is essentially a double. So what you do here, you read two floats, transform them into a double, you perform the plus operation, and then you transform it back into a float and store it into the array. Whereas on the right-hand side, in the SIMD world, this also computes on floats. Right? So it will read two float vectors, do a vector plus operation on these float vectors, and store the float vectors again. So you might actually see slightly different results from the left and from the right loop. So you have to be aware of this. But on the plus side, you will see significant speed up if you use SIMD extensions. So let's do a slightly more complicated example. Right? This is very straightforward. Let's look at something that actually has some control flow. I said before, doing control flow is difficult. So here's a very artificial example that tries to bring this home. So again, we have the same setting. We have array A and B. They're float 32 arrays. We create a new array X, which is also a float 32 array. And then we have this loop. But now inside of the loop, we have some control flow. There's a conditional in there. So whenever A of I is greater than 10, we will actually add B of I and B of I. And otherwise, we'll add A of I and B of I. Right? So we perform two different things depending on the value we found in A of I. So how do we do the SIMD style? And this makes use of our select operation. So the idea here is, instead of having control flow, you simply compute both results. So first, you assume that A of I actually is greater than 10. And that's what computes this xt here by adding B of I and B of I. Then you assume that it's not greater than 10. And you compute adding A of I and B of I. So now you've computed both cases for all 4 elements. What you have to do now is you have to blend the right parts to get the actual correct result. For that, you first compute your predicate, which uses this greater than operation. And that returns you a vector of Boolean values. And lastly, you can use this vector using select to actually blend the xt and xe results into your final result x, which will have the same values as on the left-hand side. Right? So you transform your control flow, your conditional, into what's called data flow. Right? You compute multiple values and then merge the correct results. Obviously, the code on the right-hand side computes more than the code on the left-hand side. But it computes 4 elements at a time. Right? So if you're lucky, this is still worthwhile. Depending on the code, it cannot be worthwhile. And that's why doing this automatically is really difficult. That's what makes auto-vectorization hard. But for a programmer, if you look at the code, you might get an intuition whether it works or it doesn't. So this is SIMD programming. There's a lot more to be said about SIMD programming, and there's a lot more to be developed in the area of SIMD programming. This is a relatively recent effort. The proposal is on the ECMAScript website, and it's open for comments. So it's not by me, but still, if you have any comments, I think those are greatly appreciated. There's also an effort by Intel and Mozilla to actually implement this. So this is the bug in Bugzilla you can follow to see where that's heading and how far they got. There is an implementation as a JavaScript library. So you can download that library, which will act as a shim for the functionality, and you can start playing with it to get a feeling how to program. And that's also linked at the ECMA Strawman site. OK, let's talk about parallel JavaScript. So that's what I've been working on for the last 3 years. If you have SIMD and you have these small vectors, that's already quite powerful. But what do you do if you have larger data, larger arrays, if you have more than 4-element vectors? Right? How do you program that? How do you then make use of your SIMD units, of your multi-cores, of your GPU? And that's a question that we aimed to answer when we started the project a couple of years ago. And we came up with parallel JavaScript, which was formerly known as RiverTrail. So RiverTrail was the prototype we did, and parallel JavaScript is the actual implementation we're doing jointly with Mozilla in Firefox. And parallel JavaScript operates on n-dimensional arrays. So it's arrays of numbers or arrays of numbers. So nested arrays, essentially, that's what you can think. And it's still kind of a SIMD style idea, but it's a bit more general. So you can have control flow. It's not exactly the same operations on every element. And it's designed to run seamlessly on CPU and programmable GPUs. So you write your code once, and depending on the hardware you're running it on, it will run on the CPU or the GPU. Also depending on your browser implementation, obviously. So let's look at the API. Essentially what we've done, we've taken existing JavaScript arrays and the upcoming typed objects that was formerly known as binary data, which is a superset of typed arrays, if you wish. It's like C-style structured data in JavaScript. And we've added a couple of methods to that API. So we've added a build par, which allows you to construct a new array in parallel, a map par, which is a parallel version of JavaScript's map operator. We have a reduce par, which is the parallel version of JavaScript's reduce operator. We have a scan par, which is the scan operation. So scan you can think of like a prefix sum. So instead of computing one result, as you would do in reduce, you also keep all the intermediate results. Then there is scatter. That allows you to shuffle arrays in parallel, so you can reorder things. And then there's filter, which allows you to take things out of an array, so you can drop elements from an array. And we believe this is the required set of primitives you need for most applications, for most algorithms. It might not be all of them. We're still learning. We're still looking at use cases. But these are the ones we so far identified as the building blocks for writing code. So let's again look at an example. This is a parallel map. And if you've written code using the existing map, you will instantly understand what this does. Right? We have an array A, which has a couple of numbers, 1, 2, 3, 4, 5, 6. And then we apply this function that's passed as an argument to map par here to each element of that array, and that produces the resulting array. So it's just an increment. And if you would write that today in JavaScript, it would not actually look that much different. Right? So this is today's JavaScript map. They look exactly the same, except for 3 letters. There's a very big difference, though. The top one will run in parallel, and the bottom one runs sequentially left to right. However, for the top one to be able to run in parallel, there's one restriction you have to adhere to. And that is what we call temporal immutability. So what is temporal immutability? The idea is that during parallel execution, your global heap is immutable. That means your little callback may not modify anything from the global scope. It can allocate new objects, it can change its local state, but it may not change anything from the global scope. That's the only requirement we have. So let's look at an example that would not run in parallel. This is another way to write increment, and I would ask you not to ever do this, but it's valid JavaScript code, right? So again, we have this array A with 1, 2, 3, 4, 5, 6, and we apply map to it, but we give it this little callback function here that applies the plus plus operator to AI. So what this does is it will increment as a side effect the original A, and it returns a new copy with the incremented values as the result of this map operation. So this is a side effecting operation. While this is perfectly legal, not fine, but legal, to write in JavaScript, this will not run in parallel. So the browser will tell you that this cannot be run in parallel because there is a side effect. Right? And that's all you have to remember about temporal immutability. That's all you need to take care of when you write parallel code. Let's look at another primitive, reduce. So again, this will look very, very similar to existing JavaScript. So let me show that to you. This is existing reduce. You essentially have the same callback functions. You give both of them. They take an A and a B, and they add them. Right? So this is the sum. It will compute the sum of all elements. But again, there's an important difference in the parallel version of this. Because we run this up here in parallel, we cannot actually tell you whether something is the current or the previous value. Right? If you look at the JavaScript semantics, reduce is defined as the callback will get the previous value, the previous result of the callback, plus the current element we are reading. Because reduce goes from left to right. Parallel reduce doesn't have a notion of left to right. It just reduces in parallel. So A and B might be intermediate results. We cannot tell you it's the previous result. So that's something you have to keep in mind. Also, your reduction operation has to be associative and ideally commutative to make sure you always get the same result, because we might perform them in any order. But again, that's all that needs to change. The code doesn't really look that much different. Let's look at a slightly more complex example using typed objects. So typed objects bring C-style structs to JavaScript. And how many of you are familiar with the typed objects API, having looked at it? OK, that's the minority. You should look at it. It's a great thing in the making. So essentially what you can do is you can now define types in JavaScript for data, right? So what this up here does, the first line, it creates an array type of uint8s, and it's 4 of them. So this creates a 4-element uint8 array type, right? It doesn't create the actual array. It just creates a descriptor for that type. The next line here, what I call image, creates an array type of these pixels with the 2 sizes, right? So this is a 2D array of pixels. What this describes is essentially the same type you have for the data you get back from Canvas today. But today, the Canvas data is this long, flat array, and you have to compute yourself where each pixel is and which one's the RGB and alpha. As soon as you add this type descriptions, the JavaScript engine actually knows what it's looking at. It knows it's a 2D array of 4-element vectors. So it can do all that index operations for yourself, by itself. So you don't have to think about that anymore. So let's assume we have this I here, which is just a result of getting that image from Canvas. Right? So we now have a 2D array of pixels. How do we do grayscale? And with our new API here, it's just a call to map. So we take the image, we apply map to it, and we have to tell map how deep we want to map into the image. Because as I said, it's a 2-dimensional array of pixels. So we have to know whether we want to look at rows, pixels, or single values from the pixels. So the 2 here says you go look at every pixel with your map. So this callback here gets a v, which is a single pixel. And then we can just compute the luminance, which is what this lum is here, by multiplying the different R, G, and B values with their relative factors. And we get back a luminance, and we return a new RGB alpha with this luminance value. And this will produce a grayscale image. Thank you. So, and the cool thing about this, it will do it in parallel, right? Of course, grayscale is not really the most exciting thing you can do, but if you do more complex image processing, it doesn't fit on a slide, right? So we have a tutorial where we do 3D enhancement and all kinds of operations you can do on images. And it's always based on this map-par. So we looked at another couple of applications, like we did game engine, we did some computer vision, we did 3D rendering. There's a lot you can do with this parallel computing, especially in the graphics and computer vision and 3D areas. I think both SIMD and data parallelism can give you great speedups. So there's a lot of exploration yet to be done in what you can do with parallel compute in JavaScript. And I would like to all invite you to actually take a look at that space. So there's more on parallel JavaScript. There's a Firefox implementation that's ongoing. So if you download nightly, you get the Parallel API on array today. That's in there. The Parallel API on binary data is not yet finished, as is binary data or type objects. So those two parts are still under development. There also are ECMA proposals. So there's a proposal for data parallelism that's up for comments. So if you have anything you would like to have changed or any idea what should be different, now's the time to get involved. Also, there's the proposal for typed objects, and that's actually on the way to the next JavaScript standard. So you can still get involved, but you're really late in the process. OK, with that, let me conclude. Concurrency is a given in web development. So if you're a web developer, you're doing it all day, right? You're writing concurrent application. That's nothing new. Just be aware of the concurrent semantics. It always looks very nicely and very deterministic, but it might not actually be as deterministic as you think. Take a look at promises. I think promises are a great thing to handle errors and asynchronous flows. And don't forget about web workers. They've been out there, and give them more love. They're great for running long-running tasks. Similarly, if you want to look at parallel computing, there's something I for sure will happen in the future. This will become more and more important. Web workers are there today if you want to do task parallelism. SIMD extensions are on their way. It's early, but now is the time to get involved. Now is the time to play with this. And parallel JavaScript, if you want to do parallel computing on kind of larger objects. And that's all I had to say. Well, thanks for listening. And if you have any questions, I will be still here.